All right, hey everybody. All right, so our last video for the series, we're going to look at the new version of Diane. This seems to be one of my more popular videos for some reason, so you guys must really like it. So a new version of, exciting version of Diane just came out at ASMS about a month ago. It's 1.9.1, and it has some new exciting features like data viewer. So it has Skyline and its own viewer built in. Super exciting, and maybe a little more sensitive or a little less more accurate. I believe there's some information on what has changed in the new version. But basically how you download it is you go to this website on GitHub, or you could just like Google search DIANN. And again, what DIANN is, or Diane, is a free software to search our data independent acquisition data, or the data we generate 99% of the time in the core, and you can do it for free. And so you don't have to pay me to use Spectronaut. I really like Spectronaut for a lot of reasons, but you may like to you may like Diane. And so anyway, you could download it and install it, and it's very easy to do, and it installs on Windows. You can create a desktop app, so you just click it and it opens, and I will tell you how to use it. It's very similar to my old Diane video. So if you downloaded that, if you've watched this before, that should be very, very similar. Okay, so when I opened it, you could see it already found Skyline Daily. So Skyline Daily needs to be installed, but there's a little trick to it, and it took me a day or two to figure it out. So Skyline Daily needs to be installed. However, if you go to the discussion on the GitHub, and I believe this might be closed. Skyline. Let's see here. Oh, here's some new versions of Skyline. I mean, not, sorry, Diane. It's a long day. Okay. Not generating output. Let's see. So there's a thing you have to, when you download Skyline Daily, I don't think this has been fixed yet, but it will be fixed eventually. So you need to download a specific version of Skyline Daily in order for Diane to see it. And so in order to download Skyline Daily, you go to skyline.ms, and you need to sign in to access the daily download link, and I have already signed in. And so the one you want to download is you want to download administrator only install. You don't want to just download this one. If you do, it won't. I do not think it'll work. So you have to download administrator only install, and then hit agree, and it should download as a file. And you will have to install this as an administrator, I think. So if you don't do that, if you just download the regular Skyline Daily, I do not believe it works. But once, because that threw me for a couple days until I figured it out. And you know it works because when you open Diane, it'll tell you Skyline Daily found. And if it doesn't tell you that, I don't think it'll work. Okay, so what we're going to do is we're going to drop in those .d files that I used in my last video, the normalization video and the Fragpipe video. And I believe those are here. It's these files here. There should be 8 of them. 1, 2, 3, 4, 5, 6, 7, 8. Okay. And you load them by making sure you hit the .d and not raw. So usually raw, when people refer to it, is a thermo. But we're using Bruker, and that's a .d, and you know that because they end in .d. Okay, so Diane is usually a 2-step process, so it's something to understand. So what it does is it takes a FASTA file, like it could be a whole proteome file, and predicts it. So it takes it takes the proteins and the peptides, and it theoretically predicts what the spectra should look like. That's called a predicted library. And so what you want to do is download that FASTA file, and it can be, remember we go to Uniprot for this, so we go to uniprot.org, and here's the link for human, but in order to find it, you go to uniprot.org, species. You can do whatever species you want. We're using human, so we type in Homo sapiens. And it's uniprot number 5640. Usually I like to download 1 protein per gene sequence. So you just hit download, and that'll download as a FASTA. It'll be zipped, and then you just unzip it. So 7-zip extract here. I love 7-zip, and boom, and now you'll have something called uniprot 5640.9606. So you go here, download. That'll be your FASTA. I also like to add a universal contaminants, and again, I think this is in another video. DIA universal, if I can spell that right. And there's the publication, and there's actually a GitHub site here. There's a great publication. You can find the FASTA here, I believe. Oh, look, they have different ones for tissue contaminants. I like the universal one. And so that's here. You could download the FASTA. So I usually add that too. So I added 2 FASTAs. And then you want to click this button, FASTA Digest for library free. You want to tell it where you want to put it. Let's see, I think I have this under QC, timsTOF, DIA. Just put it somewhere. and then you give it a name, and then you hit run, and it will run for like, just do it before you go home at night. It'll probably take 4 or 5 hours for an entire proteome. And you only have to do it once, but before you do it, I almost forgot, it's probably better to click enable oxidation, N-terminal acetylation. If you're doing phosphorylation, you'll have to click this because any modifications you don't click are not going to be in the library. So if you're looking for phosphosites, make sure you predict your library with phosphosites or ubiquitination, which is what this is. You can up the maximum number of variable modifications if you want. Usually I leave it the same. Okay, after like all day or all night, it will generate a library. So you come back the next day, you hit library, and let's see where I put it. QC, under QC, timsTOF, Diane 1.9, and you'll see a stupidly named spectral library because I just named it something stupid. But I would rename it as like human, and you would add the oxidation and the acetylation and whatever else you did. Give it some stuff in the file name so you know what it was. And then you would load, the spectral libraries are .speclib, and the really big one will be your whole proteome file. The smaller one, because I've already generated it, will be just the proteins you identified and the peptides and the precursors in these files. So then you hit this one as your second step, and then make sure you uncheck this because we don't need it anymore because we've already done the deep learning. And I think that's it. Oh, you can also add, if you didn't want to add those universal contaminants, you could have done it here when generating your spectral library, I believe. Okay, then you tell it where the output goes. I already put it here. Give it an output library. This will be the smaller library that just contains your proteins, peptides, and precursors that you identified. For the large library, it then loads that library again and does a second pass. Make sure you check XICs because you want to use the viewer. Make sure your threads are correct. So usually what I do is I open my task manager because I always forget which CPU I'm using on which computer. This is a Ryzen 9 12 core. It has 24 logical processors. So you want to put the threads to like 23 or else you'll only use like half your CPU. Okay, so that's good. And then you hit run, boom, it'll run, and then it'll run for a couple hours because this takes a while. Then I have one that's done already. Okay, so you see I added my predicted library. Let's see, it'll give you a warning of what mass accuracy to use. So I think for timsTOF, it generally likes to recommend mass accuracy of 15 and 15. And if you don't remember, it'll give you a little hint here when you start. It'll tell you somewhere in this text what you should do, and then usually I go, oh, and then I forget, and I hit stop, and then I change it, and then I start again. Let's see, usually it'll tell you somewhere here. See, I did it here again. Anyway, it'll tell it somewhere. Anyway, so let's look at the results. It'll run for another couple hours. I already did it. Here are the results. Okay, you'll see a bunch of, oh, let's look at the viewer first. Let's see if that actually worked. Okay, so if you want to see the viewer, once you're done, you hit viewer. This will not work unless you click that XICs, I believe. So you hit viewer. And then here's your proteins, here's your peptides, here's your files that they were identified in, which should be 8. And then you can see what the data looks like here. Oh, that looks nice. You can see it's only showing you the fragments. It doesn't, oh, look, no. Here's the MS1. It looks like it's the MS1. Okay, that's cool. All right, it'll give you the posterior error probability. So this will be your precursors and your fragments all in one go. And then these lines are what it's actually integrating to get the data. Okay, and you could see with this one, this was identified here. Oh, that looks crazy bad. This one, and then it's not even identified in these. You can see this is really sketchy. And it's probably because of this right here. See all these fragments collude? Can you zoom? Maybe. Oh, you can do your mouse wheel and zoom. That's kind of cool. This might be a peptide we want to check. This one actually looks pretty good. Okay. So, and you can see what fragment it is. Is there no precursor? Doesn't look like there's a oh, there's the MS1. Yeah, it's red. Okay. That's probably why it's collude. All right. Cool. That looks great. That worked. There's the Skyline file. Let's click Skyline. And it does something, and I think it worked before. It probably didn't work because I already have the Skyline open. That's why I gave you an error. All right, and so you can see the same data in Skyline. And here's the data in Skyline. So these are all the peptides and precursors. Now remember, a difference between a peptide and a precursor is a peptide can have multiple precursors, whether it's a charge state 2, which this is, or 3, because most peptides are usually +2, but as they get longer, they're +3 or even +4, and sometimes you will find both. Now why this is all red, I don't know. Okay, that looks pretty nice. Okay, so let's see, Fragpipe. I have the Fragpipe results from my other video, which I'll put in the comments. And let's see how this one looks. So this one is from Diane. Let's see if Skyline, Fragpipe Skyline, sees the same thing. So I will go find, and then I will type in the peptide. Don't know if you have to delete all this crap like my next video. Go find all, and it found it. There it is. Okay, and we'll close this. And let's look at them side by side. All right, look pretty similar. So 8 minutes, 8.5 minutes, 8.5 minutes. You could see, which is interesting, the Diane one. So it is using Y108743 and B3. And remember, this is the secret to data independent acquisition, choosing the right fragments. That's the secret. And this one, see what it used, which is like all of them. So it's using 1, 2, 3, 4, 5, 6, 7, 8, 9, a lot. Why Fragpipe's using all of these? I don't know. Probably because of the pseudo DIA tracer. I personally don't like that, to be honest with you. Here's what that looks interesting. Here's what this is the predicted one? This must be the predicted one, right? The predicted library from Diane. And this is not the predicted one. This would be the actual pseudo MS2 Spectre from diaTracer. Don't worry. Once you get the hang of this, you'll understand what all of this mass spec jargon crap means. So that looks really different, but it identified the same thing. And remember, everybody, that identification and quantitation are different things. And so you might want to identify something with more fragments, but only use 3 fragments to quantify it. Okay, so that's pretty cool. Do you see how it says has the ion mobility values here? And I don't see that here, but it does have the ion mobility values in both of them. I've checked, but I don't know why this is a little different. I believe I also have Spectronaut results for this. Oh, let's look at, so remember in the Skyline video, the Skyline, the Fragpipe, Diane, diaTracer, Diane, implementation identified around 2,800 proteins. Let's see what the Diane identified. I think Spectronaut, let's see, this one identified around, let's see, precursors. Why does this say 0? Why does it say 0 proteins identified? That's not right. Why does it say that? I don't know. That's interesting. Let's see. Come on. Oh God, why did I load that huge thing? Report stats. I don't know why it says protein 0. That's interesting. Let's see what the report says. So the PDF report is reporting total quantity, MS2, total quantity, MS2 signal, precursors, where are the proteins? That is so interesting. I don't know why it did that. Huh. Protein groups, IDs. See, here it's going to be around 3,000 or 4,000, the same as Spectronaut. I don't know why this is saying 0, but we can look. Oh, gosh, let's get an idea here. Let's look at the protein group matrix. That will tell us. All right, so it is reporting about 3,941. 3,940 because there's a header protein. So close to 4,000 proteins total across all the data sets. And remember, report protein group dot matrix is the quantitation expression values. So those are the ones you want to use downstream in your statistical software. All right, where did it go? I just lost. Where did it go? Diane, where are you? Okay, so that worked. So we got around 3,900 proteins. Here, we're going to look at this one, this peptide. Here is, let's see, where'd it go? Oh, I lost it. Did it break? Oh, let's see. Where is that one? I believe I'm looking at the wrong screen here. Okay. Yes. Okay. So let's look at this peptide. This is the same from, I have too many computers open. All right, we're going to look at this peptide. This is it under Diane. This is the Fragpipe one, and let's look at it with Spectronaut. Again, remember, we go peptide sequence, go to assay, peptide sequence, type it in, and delete all the crap like the numbers and the flanking and previous amino acid. And let's make sure we're looking at the right file. This is file 3670. Are we looking at the same file? That would be nice. We made sure we did that. We are not. So let's make sure we're looking at 3670. now we're looking at the right data. So this is 3670 for this peptide. Looks good. 3670 looks good. Stop. I have to wave around like a crazy person so my light turns on. All right, and then we're going to look at it under Spectronaut 3670, and there it is. All right, boom. So Spectronaut is using Y7, 10, and 8, so it's only using 3 fragments to quantify, as opposed to Diane, which is using Y10, 8, 7, 4, 3, and B3. And then this one's using, God, it's using like all of them. So anyway, let's look at like a sketchy one. No, it's not hard to find sketchy ones. Let's see. Oh, there's not even data there. Why is that? Yeah, she looks good. Usually it's easier to do Fragpipe since it was the least sensitive. So remember, Fragpipe is only like 2,800 proteins. And that actually looks pretty decent. Let's pick one that looks kind of sketchy. Yeah, that looks kind of sketchy. Let's look at that one. And we'll hit find, Control F. Skyline's a little easier because it can find anything. I wonder if we don't have to delete all that crap. It didn't, we didn't. All right, so there it is here. Boom. That's the same one, 3670, 3670. So 7.4 minutes, 7.4 minutes. You can see they look a little different. This one is using fragments. Oh, a bunch of them. This one, Diane is using 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6, 7. Pretty similar. This one, I think, looks a little better. Don't you think? I think so. Still, they still look a little sketchy. All right, so let's see what Spectronaut looks like. I like Spectronaut the best, but that's just me. But then again, it's not free like the other two things are. Okay, so we'll delete all this. And we'll look at 3670, and there it is. Boom. All right, so let's see, we can compare it. Those are the two. They all identified the same data, the same thing. Now, which one's going to be better at quantifying? I don't know. This one is using, looks like Spectronaut usually picks 3, I guess. So 1, 2, 3. Anyway, same. So they're all picking out the same peptide, identifying the same thing from the same data. So that's good, I guess. Either they're all equally wrong or they're all correct. I don't know. Anyway, that's the new version of Diane. You can watch this with my previous Diane video to get a more in-depth view of it. But that's pretty much it. And let's look at the viewer. Can we find this on the viewer? So let's look if we can find precursor. Delete that, and we'll delete that. And can it find it? In the viewer, did it? I guess no. Why did that not work? I don't know. I guess you can't find it there. Where do can you find stuff? Looks like you can't. Doesn't look like there's a find function, which is could be annoying. I don't know. I don't want to look through it and try to find it. Is there a Control F? No, no Control F. So it doesn't look like there's any kind of finding feature that I know of, but maybe there will be some soon. I don't know. Or I think there's a way to view this in a relational database, I think, a Parquet file. I think this is a viewer, and I think there's information on, if I'm remembering now, I think I'm remembering correctly now, there is, I think this is some sort of relational database, and you can load it in other software and try to find this peptide. So I don't think it's really that hard. Okay, anyway, that's it. That's how to use Skyline. The take home from the new version of Diane is use Skyline daily. administrator install, load your .d files or raw files, predict your spectral library first, do the second step where you load your spectral library, turn off this stuff, boom, you're done. And then you can look at your data by looking at Skyline, which is what I recommend. And if we've generated Spectronaut data for you, you can see if it matched. So that'll be super fun. So I would recommend when you get data from me, get the raw files or the .d files and do this procedure yourself. View it on Skyline and try to see if you have any questions, or it's the best way to learn what data independent acquisition is or the type of mass spectrometry as proteomics nerds do now. Okay. All right. Thanks, everybody. I'll see you next time.